my name is Dimitris Bralios, and I'm going to be presenting our paper titled Re-Bottleneck, Latent Restructuring for Neural Audio Autoencoders. We've seen that neural audio autoencoders and codecs have become foundational for audio processing, powering tasks such as audio generation, both using next token prediction models as well as latent diffusion models. They also power other applications such as speech enhancement as well as audio classification. However, there is a crucial disconnect between reconstruction-based autoencoders that prioritize reconstruction fidelity that often yield latents that misalign with our downstream task objectives. There are two existing solutions to this problem. The first one is to adapt the downstream model to accommodate the latent structure of our pre-trained autoencoder. Whereas the second solution is to retrain from scratch our autoencoder in order to get task-specific latent structure. This leads us to pose the following research question. Can we impose the desired latent structure on existing off-the-shelf audio autoencoders without incurring the full cost of retraining? And the answer is yes, by using our Re-Bottleneck framework, where we train an inner autoencoder post hoc inside the latent space of the base autoencoder. To do this efficiently, we employ only latent space training using a latent L2 reconstruction loss as well as a latent discriminator. And on top of that, we use a task-specific structural loss in order to impose the desired structure inside the inner latent space that is going to be used for the downstream task that we're interested in. We demonstrate our framework through three different Re-Bottleneck types. The first one is channel ordering. The second, semantically aligned latents. And finally, encoder equivariance. We also investigate the effect of our structured latents onto downstream generation using latent diffusion models. First, our order Re-Bottleneck orders the channels of the inner bottleneck monotonically by their importance. We achieve this using nested dropout during training, and we successfully order the channels by importance, outperforming random dropout as well as PCA when progressively fewer channels are retained. Here we see that the addition of the latent discriminator helps us extract maximum performance. Next, the semantically aligned Re-Bottleneck imposes semantic structure inside the inner bottleneck. To achieve this, we align with embeddings extracted by self-supervised models through a constructive loss. We achieve strong alignment while maintaining good reconstruction quality. The PCA visualizations here show that we improve semantic clustering compared to the base autoencoder latents. Next, we have the equivariant Re-Bottleneck, where we impose encoder equivariance with respect to transformation. For example, input transformations map to predefined latent transformations. And in this case, we map low-pass filtering to a multiplicative latent filter. And this enables us to perform low-pass filtering directly inside the inner latent space. Finally, we investigate diffusability by training text-to-audio models, latent diffusion models on our structured latents. We see that the Re-Bottleneck model that has been aligned with embeddings extracted from the BEATS self-supervised model improves performance both in audio quality as well as prompt alignment. This demonstrates our Re-Bottleneck's framework ability for rapid prototyping and experimentation. So, in conclusion, while audio codecs excel at reconstruction, they often lack the task-aligned latent structure that we often desire. Our solution is the Re-Bottleneck framework that offers a flexible post-hoc solution to adapt to downstream tasks. and this incurs only a minimal cost compared to retraining from scratch. We achieve this through targeted latent space losses, and we get channel ordering, semantic alignment, as well as equivariance. Thank you for your time, and feel free to reach out with any questions.